going to crack open the Learn modules, learn.galvanize.com. Oh, I have to sign in again? Okay, well, fine. Great. Nobody look, nobody look. Please work. All right, okay. So Unit 6, NumPy. This is the checkpoint. And we'll start with number 3. So NumPy checkpoint number 3, we are asked, a common operation in linear algebra is to calculate x transpose x for a given matrix x. Fill in the function below to perform this operation. So this one kind of assumed you knew what that superscript t meant. So if we do capital X's here for a matrix, and we do x transpose x, what we're getting at here is we're saying take x, which say x is a matrix that looks like this right here. Say it's a 2 by 2. And this, you could think of this as a NumPy array, a 2 by 2 NumPy array. If I take the transpose of this, what this means is I basically take this array and I make the columns rows and the rows columns. So basically, I take this thing and I flip it along this axis. So the result of this will be 1, 2, 3, 4. So that's what transpose is defined as. It says take this thing, make the columns the rows, and effectively then make the rows the columns. So you flip it around that axis. And to take something like this, this operation is to say take this array and perform the dot product with this second array on this side. So what we're getting at here is take 1, 2, 3, 4, that transpose of x, and take the dot product of that with 1, 2, 3, 4. And the dot product for matrices like this is defined as, I'll just write it out explicitly. In this case, we're going to get back a 2 by 2. And the way we get this first element here is we take the first element of this array and the first element of this one, we multiply those together. So we do 1 times 1. And then we take the second element of this one and this element of the second array, and we multiply those together. So we go like this. So it's 3 times 3 in this case. Oops. Plus 3 times 3. So this element of the result of this calculation is 1 times 1 times, or plus 3 times 3. The next element would be to take this row and do that operation with the second column of the second matrix. So in this case, it's going to be 1 times 2 plus 3 times 4. And the pattern then for these two on the lower part is we're going to take the second row of the first matrix. We're going to say 2 times 1 plus 4 times 3 for this bottom right one. And likewise, for this last element, it'll be 2 times 2 plus 4 times 4. And so if you do the arithmetic there, you'll get 1 plus 9, so you'll get 10 for the first element. you'll get 1 times 2 is 2, plus 3 times 4 is 12. So you'll get 14. We'll get 2 plus 12, which is another 14. And then we get 2 times 2 is 4, plus 4 times 4 is 16, so we get 20 for this last element. So this result for a matrix X that looks like this corresponds to X transpose times X, or dotted with X. Okay? So that's the result. What we have to do here is we want to implement that. And it's a little intimidating, right? Because it's a lot of flipping things around, and if you were to write manually these Python operations to manipulate an array to do this, it's kind of daunting. But we'll see that a NumPy array has some built-in utilities for doing this kind of stuff. So I'm going to open up a notebook. We'll call this day 5 scratch. And so we want to take this function. I went ahead and copied and pasted the stuff from the learn module. Given a matrix X, calculate the inner products X transpose X. So what we'd like to do is we'd like to take X, which we're given as the argument, so that's going to be that input array. We need to take the transpose of it. Now, if you have a NumPy array, it turns out that a NumPy array has a method called .transpose. You can call that, and it will do exactly this operation. It'll give you an array that's flipped along that axis. And then NumPy also has a dot function, which we can use to dot that resulting array with X itself. So that should do it for us. Let me just test it. And let me also just quickly review the documentation for dot. This gives us the dot product of 2 arrays. It says if both A and B are 2D arrays, it is matrix multiplication. So it ends up being this operation that we wrote out here. So we're just double checking that dot does as we expect it to, which is probably a safe thing to do in general. Okay? So let's try out our example. Let's create an array that's 1, 2, 3, 4, and let's feed it to our function. So as a reminder, if we want to create an array, I'm going to call this little x, mp.array. One way we could make this thing is we could feed it a list of lists, where the first list has the first row and the second list has the second row. So 1, 2, 3, 4. This would give us that 2-dimensional array, a 2 by 2. And now, let's feed it into our function and see if we get the result we expected. So that seems to match with what we calculated by hand. So we're at least on, looks like it at least seems to work. You might want to try a couple more examples just to make sure it's not a fluke. We've seen before that I've written functions up here that worked for some things but didn't work for others. But that's one way you could do this. Does that answer your question? Okay. Any questions on this? So NumPy, although NumPy arrays are not strictly matrices, you can treat them as matrices. You can do a lot of linear algebra type stuff where matrices are kind of the unit on which you operate with NumPy. It's important to note that you can do more than that with NumPy. It's not just linear algebra as a library, but you could also use it for linear algebra. Let's move to number 1 in Unit 6 checkpoint. So if I switch back over, this one asks us to use Boolean indexing to return the elements of an array that are greater than or equal to 2 times the minimum element of that array. So let's go ahead and grab the function as written. So we have this function we're trying to write, elements twice min. And again, we want to return all the elements of the given array that are greater than or equal to 2 times the minimum element of that array. So I'm going to take just to play around, I had this array x that I defined just above. It's a small array. Let's play around with it, play with some ideas. If I want to return only a subset of those elements, I can do what's called Boolean indexing. So if I were to do the following, something like x less than 3, what that gives me back is an array of the same shape, but it's full of bools. It's full of trues or falses, where true is anywhere in that array, any element for which that statement was true, that number was less than 3, and it's false anywhere where it wasn't the case. So if I put 4 there, we'd get a different Boolean array. If I put 2 there, we get a different one as well. I'll put 3 back. We can actually use that Boolean array to, in a way, slice or index the original one. So if I say, take x with open square brackets and feed that Boolean array right in, so writing something like this would have that effect. If we run that, what we'll get back are only those elements for which that was true. What happens if I put a 4 there? You get that. Now notice the shape wasn't retained, right? How could it really be? I mean, a NumPy array must be rectangular. There's no guarantee that the result of a Boolean index is going to give you rectangular results, so it's going to give you a 1D array. I think there's pretty much no exception to that, ever. But this is one way in which we can get what we're looking for, because what we're asking for is we want to write a function that returns all elements of this array that are greater than or equal to some number, but that some number happens to be 2 times the minimum element of that array. So the next question is, how do we get that? How do we get that number? We know how to index once we have a number, but now we need to obtain that number. So it turns out that there's a method of an array called argmin. Actually, this isn't really going to help us here. We could use argmin, but it's kind of a roundabout way of getting there. Let's go ahead and use the method called min. If I call min on x, that's going to give me back the element of x that is the smallest. So in this case, x is 1, 2, 3, 4. So the min happens to be 1. Likewise, there's also a max method, which would give you the maximum. So I could use this. I could multiply this by 2, and that would give me 2 times the minimum value of x. And at that point, I've basically written the code that defines the number I'm interested in using for my Boolean index. Right? I think I've got all the pieces. So let's go ahead and if I then say what I want is x where x is less than 2 times x dot min. And that piece of code would actually get us what we want. Something I want to point out is how we went about solving this problem. We didn't try to solve the whole thing at once. We took this sentence and we broke it down into pieces that we could kind of solve individually. If you guys remember on Saturday, that was kind of a big problem, right? There were a lot of little pieces in it. And it's kind of overwhelming to try to solve everything at once with one big block of code, starting from the top and going to the bottom like an inkjet printer. That's not how you typically solve problems. It's also not how you really paint a picture. You don't start at the top left and work your way all the way down to the bottom right. You work a little bit over here, then you work a little bit over here, and you kind of fill in detail as you go. We write code kind of the same way. Think of it like a painting. You kind of sketch out things with a pencil first, you separate it out into the component pieces, and then you work on those pieces almost independently. And that's what we did here. We looked at the first bit. We said, well, we'll figure out how to first do the slicing, do the indexing, and then later we figured out how to obtain the number we needed to do the indexing with. So to finish out, let's finish out our function. We're going to take array. We're going to say Boolean slice it. We want the elements of the array that are greater than or equal to 2 times the minimum of that array. And so now if we test it out, for example on x, that looks like it's greater than or equal to 2 times 1. We know that x's smallest value is 1, so it seems to check out. Any questions on that or on the approach? Okay. So with that, we'll get to tonight's material. It is something new, but not something entirely new. Tonight you'll learn about Pandas, first, where it fits into the PyData ecosystem. In my initial lecture on Saturday, I talked about kind of how the PyData or the scientific or numerical Python stack is kind of organized. The lowest level, you've got Python. If you go up a little higher, you get NumPy. If you go up a little higher than that, you start getting things like Pandas. Pandas is actually built on NumPy, and we'll talk about sort of how NumPy fits into that as we go. You'll learn how to load data into a Pandas data frame. The data frame is kind of the core data structure of Pandas, similar to how the NumPy array is the core data structure of NumPy. And this will be the first opportunity we have to actually load a data set in. We're in week 3 and we're finally working with data. You could argue that we were playing with data on the weekend, but we were generating all of that. We defined a model and we generated a bunch of numbers from the model. Often doing data science means you have data and you want to build a model based on the data. You want to go the opposite direction. And so we're going to get to the beginnings of that tonight by actually loading data that's already present somewhere into a data structure. We'll also talk about or get familiar with the various methods that a data frame has available for understanding a data set, for exploring that data set, because it's not enough to just load data into a data structure. It's also a useful data structure for understanding the data or asking questions of the data. And you put those questions in form of code. Lastly, we'll get into visualization because it's actually very difficult to ask questions of data without trying to build some kind of useful visualizations for it. Usually can't get away with just staring at numbers unless you're looking at descriptive statistics, maybe like means or standard deviations or skews or things like that. But if you want to go further, you usually want to do some kind of visualization. So with that, we'll get started. What I'd like you guys to do is a little bit different tonight. Go ahead and go to the repository where is kind of the center of this course. So I'll drop this link directly into the Galvanize, into our Slack. Hope this loads. There we go. And if you could, once you get to this page, go ahead and go into lessons. I want you to click on day 05, D05. And tonight's material is going to be found inside of, or something we'll need for tonight's material is what's inside of this data directory. And so normally for a course like this, I would have you guys install everything you need for using Git, and I would have you just clone this whole repository so you'd have it all. But for the purposes of tonight, what I'd like you to do is to download click this download button on the top right. Go ahead and click download zip. And you'll need to save that wherever your web browser saves things, probably a downloads file, a directory. If you could go into downloads, find that file. It should be called introds master.zip. And if you extract it, however you extract things, then go into that directory. Put up your orange sticky if you have any trouble with this, and we'll come by. This is the first time I've actually asked you to download something, so I understand if it ends up someplace weird. Put up that blue sticky if you manage to find your way down into this D05 directory. Okay, good. Cool, okay, good. So you guys are finding your stuff, all right. The next challenge is finding it in the notebook, the Jupyter Notebook server. So go ahead and start up a Jupyter Notebook as you normally would. I think for most of you, this is a view to your home directory. So I'm going to do the same myself. I'm going to go back over to my notebook. And for me, this stuff lands in downloads. For you and your web browser, it probably lands there unless you explicitly change that. Go ahead and find lessons D05 directly in there. So that is in your Jupyter Notebook session. And put up a yellow sticky if you have trouble finding it. We're going to need to use this in order to use the data that's in that data directory. It's going to be lessons D05. Oh, we'll talk about the assignments later. For now, just open up a new notebook. So if you would, once you get to this point, go ahead and click New Python. Open up yourself a fresh notebook. Avoid the temptation to click on lesson 5-pandas. That is basically this lesson material. But I want you guys to have the experience of going with me on a magical journey through Pandas, not just reading to yourself for 2 hours. Okay, looks like people are getting there. Again, the point of this is I need you guys to have the data that we're actually going to be working with for all this to work. We're going to be loading stuff in. Yeah. Go ahead and click New and just make yourself a new notebook for now. You can always go to that notebook later. That is the material for tonight. Okay? Okay, good. All right, we'll go ahead and get started. So tonight is all about Pandas. And you might be like, why is this library called Pandas? What is it for? I've already explained at least roughly what it does and what it's useful for. But tonight we'll actually get a sense for how is that the case. So Pandas is a fairly new library. As of about the, I guess, very early 2010s, it started to rise in popularity and become kind of well-known quantity. Up until then, people were pretty much using NumPy for data analysis. So directly using NumPy arrays to load, time series, one-dimensional NumPy arrays into memory, or if they had like tabular data, they would use a two-dimensional NumPy array for that. But the trouble with NumPy arrays is they don't really handle things like missing values very well. There's not really a mechanism for that. And also, they can't really handle, in that sense, they can't really handle ragged data. So basically, cases where you might have several observables, like time, say you were measuring temperature with time, as well as maybe humidity. And it might be the case that you have every time plotted here, so 1, 2, 3, 4, 5, 6, 7, 8, but you might have 87, I don't know, didn't take a measurement that time, 92, 93, things like that. And then maybe I didn't take measurements the rest of the time. But then I got relative humidities of 70, 85, and so on. So like a NumPy array struggles with holding this kind of data because one, it doesn't have this missing values, a way to clearly denote missing values. And two, it doesn't have labels for its axes. So if you were using a NumPy array for holding a bunch of data, like real data that had some kind of sense to what these variables meant, what these numbers meant, you'd have to hold on to this information separately. So you'd probably do something like what people did up until using Pandas, which was make a dictionary where the keys were column names, and then make a bunch of one-dimensional NumPy arrays for each one, as each value. That's kind of a poor man's data frame. So we'll see how that kind of works out in Pandas. We actually have a much better data structure for this now. And in addition to that, it also has the ability to have a labeled index. So you could, for example, make this time column an index that you could use to uniquely specify rows. So with that, let's actually do something with it. The way we import Pandas is to say import Pandas as PD. This is kind of the custom. Just as we would import NumPy as NP, you'll see that pretty much used universally by people in the Python community. And to build a data frame, we're going to see how we build one from reading a file, which is kind of more common. You're probably going to be reading an actual data set that lives in a file somewhere. But it's important to know that you can build a data frame from scratch from Python data structures. We're going to build a couple here, and we'll see how the missing value stuff plays out. I can build a data frame by calling pd.dataframe, open parentheses. This is the constructor for a data frame. And one way I could build it would be to feed it a list of dictionaries. So I could, for example, go this list, create a dictionary. For key A, we'll have value 1. For key B, we'll do value 2. For key C, we'll do value 3. And the next element of my list will be another dictionary. And this will have, for key A, the number 4. For key B, the number 5. For C, 6. And why not? For D, 7. So if we were to run this, we'll get back a data frame that has 2 rows, one corresponding to each of those dictionaries in that list, and it has 4 columns. Now, if you notice, one of these dictionaries, the first one, didn't have a D key, but the second one did. And the way that the data frame is constructed is that, well, since that first dictionary didn't have a D key, what gets put in for the D column is a NaN. It stands for not a number. This is how Pandas indicates missing values. So it's able to handle cleanly the fact that row 0 didn't have a D, and that's okay. It might be that it wasn't measured, if this is some kind of, meant to be some kind of measured quantity. It wasn't measured for that particular sampling time. There may be whatever explanation for why it's missing, but the point is the data frame is perfectly happy to accommodate this. Another way we can build a data frame, and that's kind of the way that I tend to build them, is to feed it a dictionary of lists instead. So if you do pd.dataframe, let's say A 1.4, B 2.5, C 3.6, and we're going to try this. I don't recall if it will work as I expect it to. We're probably not going to be able to do that. But I often do this. Oops, sorry. Open parentheses, not with the square brackets there. So that would be another way we could build the same data frame. Instead of feeding it a list of dictionaries, I fed it a dictionary of lists where I explicitly said, this guy is a NaN. Yes? I did something kind of a bit of a hack here, but I've used it many, many times over the years, is that Pandas at the top level actually imports NumPy as NP in the module. And so NP happens to be present in the Pandas top level namespace. And it happens to point to the NumPy library. So often I'm too lazy to explicitly import NumPy as NP. And so I will use that. I'm not going to claim that it's robust or that there will never be a time where the Pandas developers don't do that, but it's been there for years and I keep using it. So for quick and dirty code that as a data scientist working that you'll often be writing in a notebook, it's kind of okay to take shortcuts like that. If you're writing production code, like so you're planning to put something, throw it into some service that has to run endlessly over and over again for years, you probably don't want to do things like that. But for the purposes of this, where time is kind of more the factor, our time is more important, that's perfectly acceptable. At least in my view. If I was your manager, I would say it's fine. Does that answer your question? Okay, cool. Yeah. So data frame is a class. So we didn't get a chance to sit down and learn about how to write our own classes, but it's an example of a class. The way we call pd.dataframe is it looks like a function, right? Because when you call that class definition in that way, what you're talking to actually is what's called the constructor for that class. The result of calling pd.dataframe is an instance of a data frame class called an object or an instance, basically. Does that answer your question? Okay. So looks like a function, kind of behaves like a function, but if you were to ask what the type of pd.dataframe is, you'll get type, which sounds ridiculous. What that means is that this is a class definition. You can think of it as a data type in and of itself. So those are all ways you could build a Pandas data frame from scratch. We're not going to be doing a lot of that in practice. What we will be doing is reading data. So what I'd like you guys to do is to have a look at the following. We're going to use a function called pd.readCSV. Before we go much further with that, the notebook has some cute magic functions that you can use, and to call them, you put a percentage sign in. If you do %ls, and you type in, for example, data, there's a data directory in the current working directory of our notebook. If we were just to call ls, then that would show us all of the files and directories that are in the current working directory of the notebook. So by saying ls data, I can get a view as to what files are present inside of that directory. This isn't Python, this is a notebook command. It's kind of a convenience that's there. So what I'd like to do is I'd like to call read CSV, and I'm going to feed this function a file name. This is the first time we've done this in this class, where we're reading a file from our file system into a data structure. So we're going to say data/wine quality. And we're going to choose the reds for a start. And if I just run this function as it is, we get back something pretty gnarly. Doesn't really look that useful. It is a data frame, but all the columns look like they're pressed together into one, which is kind of pointless. We've got one yellow sticky there. I don't know if, Aniket, you got a moment. So what we need to do to this function is we need to feed it some parameters. We need to feed it some arguments to tell it to do the right thing. If we have a look at this file, and there's another magic called cat. If we call cat, this will actually show us the contents of that file printed out. Cat stands for concatenate. It's similar to the bash function cat. And so if we look what this file looks like, it's got what appear to be column names, fixed acidity, volatile acidity, citric acid, and they're all separated by semicolons. And it looks like the actual values in each row in this comma-separated value file aren't separated by commas, they're separated by semicolons. CSV files, or comma-separated value files, are some of the most common ways to put tabular data in a file. It's pretty ubiquitous. It's kind of a terrible data format because it tends to balloon the size of things. Floating point values are defined as far as they're actually literally defined in there. And it's defined as text. So 7.4 is defined as the text 7.4 as opposed to the number 7.4, which would be a lot smaller in memory. But all of that aside, CSV files are still very common. And there's some advantages to them in the sense that you could always write a parser to parse that stuff out. If it's in some binary format, sometimes it's kind of lost to you if you don't have the code that actually can read it. So there's advantages and disadvantages to this, but the point is you'll find them everywhere. And so there's a reader built into Pandas for reading CSVs for that reason. And this reader is pretty flexible. One thing we can tell it is what the delimiter is between values. So if we say the delimiter is a semicolon, now we run this, we get something that looks a lot more useful. Our data frame is actually built in the way we would expect it to be. Now just running this function creates a data frame, but in order to use it, I should probably attach a name to it. Remember, there's objects and names in Python. So far, we just created an object and looked at a visual representation of it. Let's attach the name df to this. It's often the case that we will use df for a data frame simply because it's a generic name, and we usually run out of creativity when calling our data frames different names, so we usually use something like df. And so now we can refer to our data frame directly. Now it's being held in memory. If you have a giant CSV file and you try to read this in, then you're going to use up a lot of your computer's memory. And so if you start doing some data science projects where you're reading in things, you might notice that you actually could hold a pretty big data frame in memory. But it turns out data frames, when they represent things like floating point numbers, so let's look at some of the methods here, like dtypes. Looks like most of these columns got interpreted by the CSV reader as floating point numbers, so 64-bit floats. So the data frame's actually representing these numbers in a pretty efficient format. It's not representing them as text, unlike the CSV file. I've held data frames that are more than like 2 million rows in my laptop. So it turns out you can handle some pretty sizable pieces of data, things that would be too big for Excel, for example, just fine with a laptop with, say, 8 gigs of RAM. And that's one of the advantages of using something like Pandas over something like Excel. You can hold much bigger data sets and do a lot more with them than you could with a tool like Excel, which tries to render everything as well as hold it in memory. Any questions so far? Is everyone able to load a data frame? Red wine data? Is anyone not able to? That's the better question. Okay, good. So we're at about the 45-minute mark. Let's go ahead and take a 5-minute break, as usual. We'll meet back here at 6:50. Question. I think they might, but they're generally built to be cross-platform, so they probably wouldn't be built to be dependent on that. I'm willing to bet they're written in Python, so they probably call, like ls probably calls os.listdir, which should work across all platforms, because those aren't written to depend on Unix binaries that would be present on like a Unix-like system. You can. Yeah, there's actually a run method, or run magic. Run the name file inside of Python as a program. So if you had a Python script and you wanted to run it within this Python interpreter, then you could do that. It would just execute all the things in there. Oddly enough, there's also at least one shell written in Python. So if you're familiar with a Unix shell like Bash, I use Conch. Conch is a shell that's kind of Bash-like, but it's written in Python, and it basically is a Python-ish shell. For example, the loops. It's kind of like Bash, kind of Python, but also kind of neither. So it's a very weird shell, but it's cool because I can write, so I have some Python libraries I've written and I could just import them, for example. So I could say import numpy as np. Boop. Yeah, so I could work directly with numpy arrays or I could read in CSV files in Pandas directly in my shell and then do things with them. It's cool, but in practice, that's kind of like, well, I'd rather just have like just a Python interpreter. But